A warm welcome to this presentation. This is Mr. Shin paper ID 1950, presenting designing a mapless navigation mobile robot using deep Q learning. Here is a outline of my presentation. With the advances and innovation in computer vision and electronics technology, the processors are becoming more and more powerful. Hence, the processor used in robotics technology are very common and very powerful. Hence, the robots are becoming a part of our daily life. Some examples are personal robot PR2 or a Roomba. Cleaning dust cleaning robots are very commonly used in household and office based environment application. In indoor environments, the navigation of a mobile robot is very difficult. So multiple algorithms and techniques are being developed, which we have performed an extensive literature survey on that. What we found is reinforcement learning, which is a branch of machine learning, is a best suitable case in case of robotics, as the data set present for a robot in an environment is there is no map or initial state for a robot is present. Hence, using a reinforcement learning, we can perform a good level of navigation by using a deep Q learning strategy, that is DQN network. Currently, in case of robotics, there are multiple algorithms which are used for navigation, such as fuzzy logic, PRM, or SLAM. SLAM is the most used algorithm for the localization and mapping in an environment, but the SLAM has multiple problems. There are multiple techniques such as visual SLAM or point cloud based SLAM using the RP lidars. There are many techniques such as G mapping, RTAP map, hector SLAM. We did an extensive literature survey on all these techniques, but we found that SLAM has multiple problems. The main problem is SLAM is like a chicken and egg problem, where you don't know the map, as well as we don't know the initial position or its localized position in an environment. So that is the biggest problem. So finding an initial position is a very difficult. So in case of a dust cleaning robot, we saw that the owner moves the robot in a household environment with the help of mobile application in order to create the map first, and then the robot uses some kind of algorithm like a star or digicastra to explore the or the move in an environment. Okay, so that's the biggest problem. Then the second problem is of a loop closure. So if, let's say, robot is inside enclosed environment of four walls, or with all four walls of same color, then robot get confused about its localized position. Also, if there are less features, landmarks, or objects in an environment, robot is very much confused about its position in an environment. Also, the SLAM needs more accurate sensor, whether it is a visual SLAM or the LiDAR based SLAM, that laser based SLAM. It needs very accurate sensor in order to create an accurate map, so that it can move in an environment very accurately. So as we can see, there are this kind of problems are there. Hence, this is typically a case of the reinforcement learning and not of supervised or unsupervised learning, because here we do not have a fixed data set or a map of environment. Completely, the robot is blank in an environment, and we have to explore the environment in order to find the best possible navigation strategy. Hence, we are using DQN, that is Q learning strategy. So, the primary aim of our research is to achieve the autonomous navigation by navigating the robot towards its goal without hitting an obstacle. So, here we are making use of a TurtleBot 3. We have also designed our own TurtleBot kind of a robot with the RP LiDAR A1, NVIDIA Jetson Nano as a computational board, Arduino Mega as a lower control board, the encoder motors, the IMU as a gyroscopic sensor, the BMS, and all those things. So, with the help of Q learning strategy, we are trying to implement this algorithm. Q learning is an off policy value based reinforcement learning algorithm. Why it is off policy? Because it randomly chooses the state action set from a memory rather than particularly exploiting. Okay, so for using Q learning strategy, we are making use of a Bellman equation. So Bellman equation is basically an optimality equation for maximizing the Q value or maximizing the reward function. So basic goal here is to navigate the robot by maximizing the Q value, maximizing the reward, and reaching to the goal as soon as possible. So that is the main goal without hitting an obstacle. So in case of Q learning, we are making use of a Bellman equation, where we are finding the new new q value or next q value by iteratively processing the batch of current q values. So the formula is current q values plus the alpha, which is the learning rate, times the reward for taking a new action, plus the gamma, which is the discount factor, times the maximum expected future rewards minus the current q values. Okay, as we are making use of a turtlebot 3, it has total 5 output states which are applied to the motor, either right, left, forward, that is front, forward right, or forward left. Okay, then these are the 5 action sets which we will get at the output of a neural network. But what are the inputs which we have are the lidar. From the lidars, as we are using the lidar sensor, total 24 LDS value we get per rotation. Secondly, the distance we get from a odometry, that is encoded odometry sensor, and from the IMU sensor we get the angle towards the goal. So these are total becomes the 26 states as an input to our neural network. So this is the structure of our neural network where we have a 26 input states. There are some hidden layers, and at the output as action we get the 5 states which are left, right, forward, forward left, and forward right. So this is the algorithm which we are typically following here for q learning implementation. So initially what we do is initially we choose a random action, either by exploration or exploitation, because here we are using an epsilon greedy strategy. So what epsilon greedy strategy does is it basically explore the environment as well as the exploit the environment. Why it is necessary in case of robotics? Because then if the robot is always taking or always exploiting the environment, it will not be able to properly train. That means it will only take those actions which will give the robot maximum reward, but then our training will be very poor and the robot will not be able to perform well in any other environment. Okay, so that's why epsilon greedy strategy is important. So epsilon greedy strategy sometimes uses a Bellman equation to find out the best optimality value of q value in order to maximize the reward, and sometimes it randomly chooses the action from a state action pair in order to explore the environment. So it keeps a very good balance between the exploration and exploitation. So we randomly choose the initial action, we perform that action, we look for we observe the reward, and based on that observation we store that observation in a replay memory based on the reward we got. Then we iteratively choose a sample of then we sample the batch from a replay memory, and we sample it and pass it to the second layer in order to find the output action. Okay, in order to find the best reward based on the strategy, either the reward we get maybe a positive or a negative reinforcement. If it is an exploration, we might get a negative reward based on the function. Okay, so by using a gradient descent strategy, a gradient descent algorithm, we iteratively find out these things. Instead of value-based iteration, we are basically making use of a neural network in order to fastly process these values and find the output actions. Okay, so in order to robot, we also need some kind of a reward policy. So whenever the robot reaches the goal, we are giving a plus 100, and whenever robot hits the obstacle or it is randomly moving in a state space, we are giving minus 100 as a negative reinforcement. So this is a reward strategy. If the angle of the robot is greater than minus pi by 2 or less than pi by 2, then the reward from angle will be greater than 0, or else it will be less than 0. If the distance, that is current distance of a robot, is less than the distance from a goal, we give the distance of reward greater than 2, or if it is else it will between 1 and 2. So these are the basically reward functions or reward policies we have designed for our particular robotics case. You can read it out. At the result, what I would like to say is, after performing up to 700 episodes, the robot is perfectly trained, and robot is able to reach the goal without hitting an obstacle with as much as fast time. Okay, after 700 episode, though the robot is not much more exploring; it is directly exploiting because it is much of a train, so it is fastly moving towards the goal. So these are some of the hyperparameters of our neural network. You can see we have kept the 6000 as our episode step. So total 6000 steps it can take in a state space by randomly moving for one episode. Okay, so multiple episodes are done, up to 700 episodes are done to train the robot. So after 700 episodes, the robot was much more able to explore, exploit the environment without a problem and reaching the goal. So after performing this research, we what we conclude is there are some improvements which can be done. So as we have the weights and epsilon values stored into the JSON format, then these values can be ported to actual turtlebot or our own designed turtlebot 3 to perform in a real world tasks. Okay, designing our own robot we did because the original turtlebot 3 was very expensive. Also, by designing our own real world robot, we can adjust the computational power as per our need, like a GPU and all those things. Instead of using an epsilon greedy strategy, there are some better strategies which we can implement, because epsilon greedy strategy is not always the best option, because after sometimes the robot becomes so greedy that it only tries to exploit the environment instead of explore the environment. So that is becomes a problem. So instead of q learning, as in case of q learning, we are only dealing with discrete values. We can use a ddpg, that is deep deterministic policy gradient, or algorithm like soft actor critic to improve the overall experience, which deals with continuous state action space, which is much more give outcome with the help of motors. So some sensor fusion technologies also can be used with the help of visual slam and dqn. Combining together will uh, gain a more proper results or improved performance in a navigation. So that's a bit about what we did in case of our project or research. So these are some of our references. Thank you so much. Have a good day.